Generally, you have all of this very expensive, very complicated test equipment, which then you need to hire specific programmers to write in those languages. Like we said, with the maker movement, all these different devices came out, the Raspberry Pis, the Arduinos. And so you couple that with a couple lines of code, and now you're able to drive all your test stimulus into your board as you're designing your board.
Hi everyone, it's Judy Warner. Welcome back to the OnTrack podcast. We're happy to be back with you and geek out again with another wonderful guest. This week we're talking to Ari Mapora, who is the embedded software engineer at Virgin Hyperloop. He's going to talk about test-driven development for embedded systems and how to ease that process, cut your costs and time, and make things a lot easier. So lean in, enjoy. I'll see you on the other side. Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Hi, Ari. Thanks so much for joining this week. We're so glad to have you on the OnTrack podcast.
Thank you. Thank you. I'm happy to be here.
Well, you and I were talking last week about an article you wrote for Altium. But before we talk about that, why don't you give our audience a sense of sort of your background and your expertise and sort of tenure in the industry?
Great. So my background is in both embedded hardware and embedded software. I'm crazy about embedded systems. I love both the electronics design aspect of it. I love the software side of things, whether it's writing the FPGA code or embedded C, or even just the testing of it, integrating board bring up, all of that, the whole ecosystem, and being able to play with hardware, but have that instant gratification when you write software too, and being able to see LEDs just blink and the basic things in life that kind of make you happy. My background is primarily in military and aerospace, working on different type of embedded applications, power systems, radar systems, communication devices, things like that. And so recently I've been working on devices that have FPGA and processor fabric together, and trying to come up with more novel ways of being able to develop embedded systems with a lower cost solutions and environments, and with different test-driven applications that can make it easier for the designers.
Well, as we were talking earlier, I'm going to give my disclaimer here. This is not a subject I understand, but I appreciate the things that you have taught me, as well as Jeremy Blum. And I think this is going to be really, really helpful to our audience as far as easing this path instead of sort of the current prevailing way we do it. So again, you wrote this article, and your article goes in far more depth than we have time to do on the podcast today. But I wanted our audience to sort of get a sense of what you're talking about. The name of the article is Low-Cost Solutions for Automated Hardware-in-the-Loop Testing. So talk about kind of why you wrote this article in the first place, and define the problem that you're trying to address in this article.
Yeah, so first of all, I have to admit it's a little bit of a mouthful. So maybe we'll dissect it a little bit. So hardware in the loop testing is basically, if you can look it up online, you'll see that the concept is having testing done with hardware in the loop. So you're not simulating your tests. You're not manually, also when you do it in an automated fashion, you're not manually testing your devices. This has been kind of a pretty standard, industry-wide standard system that's happened for quite some time. A lot of, especially big integrators, in military, aerospace, or even internet-connected spoons or basic devices. Everybody has a lot of experience with hardware in the loop testing. What's novel about this and what I'm providing is really taking that level of rigor that's done in the aerospace or the military or commercial sectors And instead of taking very expensive, very onerous processes in order to create all this automated hardware in the loop testing infrastructure, both on the physical side and developing all the software, the cost of it can be exorbitant, is taking very, very simple, cheap devices and providing the coverage that you need, the test coverage to cover majority of your test cases. So something that you would normally, let's say, for example, invest tens of thousands or hundreds of thousands of dollars into very sophisticated test systems that would test 99% of your design, we could swap out with something significantly cheaper, like on the order of hundreds of dollars or thousands of dollars, and cover, let's say, 75%. And then that last 25% can be done manually or with more sophisticated systems.
Okay, that's a good kind of overview. So talk about the specifics of sort of what kind of the prevailing methodology is today, and why cost, obviously you've cited. And what is the prevailing, how is it done now? And then we'll sort of contrast that against, what you're proposing here.
So especially as I described earlier, in industry, a lot of the times when you do your design, specifically with embedded electronics or hardware in general, is that you'll test it. As a design engineer, you'll design your board, you'll bring it back from manufacturing, you'll bring up your board, and then, inevitably there's going to be some changes. You have to do some rework. Maybe if it's an embedded system, you have to bring up the drivers. You might have to probe your chips and look on an oscilloscope and make sure that all the the signal integrity is good. So your microprocessor, your FPGA, whatever it is that's processing those signals, are processing it correctly. So there's a lot of investigation, a lot of bring up. What happens for the first time board bring up is that the design engineer, usually not a test engineer, but the design engineer themselves, will do all of this manually, which is fine for the first time. The problem occurs is once you start having to make changes. If you have to rework the board, if you have to start changing the drivers around, if you have to swap an IC, it could be something as basic as, you end up having like a solder bridge or some mistake across your board, and now you're hosed and you're trying to figure out, what you did wrong or what's going on.
Yeah.
And so, so the challenge here is, the challenge today is that you have the design engineer who's constantly retesting everything every single step of the way as they're developing their design. And the challenge with that is our design engineers are getting more and more expensive, and it's not quite at the stage where you can just throw it over the wall to the testing group, which is where all the automation really happens. Like I said, maybe 99% of all your design is covered. It's great. It's amazing. It's really expensive and takes a lot of time to develop.
Yeah. So let's peek over the wall a little bit. So I'm assuming expensive test and measurement equipment is used on that side, correct?
Correct.
Okay. And then something's tweaked and then they throw it back over the wall. And so time. So there's all this back and forth, very analog kind of, in old-fashioned terms, we used to talk about, instead of kind of a concurrent engineering where, like you said, it's in the loop, that it's happening kind of almost simultaneously or proactively. Is that correct?
Correct.
Okay. So you've got the expensive test equipment. Go ahead, Ari.
And one of the caveats there is, if you're coming up with a production line and all you're doing is incrementing technology or modifying or tweaking something, so you have all your production line equipment there, you're set up, you've been doing this product for 10, 15 years, that we're not talking about. We're talking about new design, the new product introduction from beginning to end, which you don't have any of that infrastructure.
Right, of course. Yeah, that makes perfect sense. So you've got, the inefficiency of time. You've got expensive test equipment. And it sounds like there's no insight from one side of the wall to the other. Is that correct? Or like, how does that work?
At best, you could have all in the same group where the design engineer can walk over to the test group. But inevitably, there's going to be some sort of disconnect between the two. Really, what you need is that designer in it 100% all in, because they're tweaking things constantly and they've got to be part of that process. But you just don't have enough time and enough people and enough effort to really put that all together. Hence the siloing of a separate test group.
So as if silos aren't problematic enough in this industry, COVID happened. And even if you were in a larger OEM where you could sit in a cubicle next to your software developers and you're a hardware engineer, that's all gone now. Now you're physically removed from one another. Has that, in your experience, I know you can only talk for yourself, but do you think that's complicated this at all?
100%. And actually, that was the impetus for writing this article, is that I was stuck at home. I had started a new job where in Los Angeles, guidelines were to shut everything down. And I was lucky if I could grab a few pieces of test equipment at best. But, we had a brand new team. We had a lot of people bringing on, and just not enough. Forget about having enough test equipment or ordering. There was a shortage of equipment. There was a shortage of office desks. There was a shortage of everything going on. And I needed to find very quick, rapid solutions that I could get the most bang for my buck. Given the nature, again, low cost, but also to automate things as much as possible, because I didn't have the whole software group and test group and everybody sitting in my living room next to me while my son is drawing and coloring and I'm trying to work on my laptop. It just didn't exist.
I know. Our whole world is so changed. It made me laugh just on a human level that when we were talking last week about this, that I'm like, oh, what's that balloon in the background? You're in your lab and there's just a Mylar balloon. You're like, oh, my preschooler just graduated preschool. And I'm like in a tank top and like, any hints of professionalism of just, our lives have become so integrated. But I think it's a really good, and I think I would love to do another podcast with you just about the lab you developed, because I got a little peek of it and you told me what you could build your at-home lab for, and we are totally going to do that. I think you should write an article about that one too, Ari. I think that would help a lot of people. Do you know who Ken Wyatt is, Ari? He's an EMC guy.
Uh-huh.
Anyways, he wrote a book about building like a lab, like EMI testing lab in his house. So anyways, I think we need to do that one. So COVID complicated it, and this was your workaround. But you sort of implied that people are starting to move in this direction anyway. So, and that there was already sort of a shift happening in this direction. A lot of people I'm talking to across all disciplines are saying we were already on our way to this thing. COVID just accelerated it by a million. Do you think that's true of this situation?
I think to a certain extent. I think it's pushed people, like I said, it's pushed people to come up with more novel ways of validating their designs while they design. But I think it's still a little bit out of reach, because what we're going to talk about today is really taking more of a software-based approach to hardware development and design. Hence the title TestDriven Development, which is something that's been in the software world for quite some time. But nobody ever talks about test-driven development for hardware systems. It just doesn't really exist at this point. And that's something I want to kind of touch upon in conjunction with all of this low-cost, automated solution.
Okay, all right. So you've kind of alluded to me that even though it sounds like it's complement, it can be, how hard is this? from where I'm sitting as a non-engineering professional, it sounds complicated.
It's much easier than you would imagine. I mean, we're talking about once you get all your equipment and everything set up, which is very, very easy, thanks to the maker movement and all the hobbyists around the world. We're talking about plugging in a device, installing some software, and even that can be bypassed, as I discussed in the article, and literally running like 1 or 2 lines of code, and then boom, you've already got like an automated test set up. And again, it's demonstrated in the article that I wrote, and I have examples over there. Slightly more complicated, but pretty trivial examples that you can see how you can run directly on targets and start testing things pretty easily.
Okay, so that's sort of the enabler that's sort of allowed for some of this disruption, right? Is that the maker movement happened, so there's more low-cost hardware or semi-automated scripting or whatever. So so that kind of leads us to things like Arduino, Raspberry Pi. Talk about what some of those building blocks that are the pieces that help enable this.
Right. So just taking a step back, like we said, generally you have all of this very expensive, very complicated test equipment, which then you need to hire specific programmers to write in those languages, things like that. So the idea here is like we said, with the maker movement, all these different devices came out, the Raspberry Pis, the Arduinos, and also other devices that can do things like, drive analog signals out and have waveform viewers at fairly high frequencies, especially for embedded systems, which is usually enough. Something like a device that I use, which is the Analog Discovery. This is a device, again, discussed in the article. This or another comparable device can send out digital signals, can send out analog signals. It can read waveforms up to like 100 megahertz, which is fairly high for embedded systems if you don't need anything super high speed. But then what the key is that you can then couple that with very, very simple Python scripts. And nowadays, even the kids are learning Python in middle school.
Yeah, it's crazy.
It is. And so you couple that with a couple lines of code, and now you're able to drive all your test stimulus into your board as you're designing your board. So let's take a step back for a second. When we talk about test-driven development, so test-driven development, the concept here is you write, in software generally, is you have a kind of a goal, like a requirement. You say, I need to, let's make it the most trivial possible. I need to print out on my screen, hello world. So instead of writing the code to say, hello world, I'm writing a test to say, hey, test, can you just go make sure to see that my computer printed hello world? So you write that test, and obviously it's going to test it, and it's going to fail because it says, nothing printed on your computer. So the idea is to first get a failing test and then write code as a companion to that. And as soon as that passes, you move on to the next thing. Oh, now I want it to say hello world Ari. So you write in the test, have it say hello world Ari, and it says, wait a second, it just said hello world. It didn't say hello world. I'm trivializing it, but that's kind of the idea.
Right, of course.
So that then stepped down a notch to lower level development, which test-driven development for embedded software. So in C, for example. So this book, for example, Test-Driven Development for Embedded C, is an example of somebody trying to take all of that test-driven methodologies, write their unit tests, make sure it passes or fails in C, and then deploy it to their microprocessor. Now, what if
time out. I just want to say to our listeners real quick, I'll link that book that Ari just mentioned in the show notes. So if you're not watching on YouTube, I'll make sure to link that in the show notes. And I think, Ari, you said that's kind of your go-to.
It is, yeah.
Okay, all right.
So now let's take that down a level even lower. Let's go down to the fundamental electronics level. What if we could kind of do quasi-test-driven development for our electronics? Well,
okay.
Which is... You could do that Until now, let's say until, relatively recently, you would buy very expensive test equipment. You would be the test engineer. So you would have to know how to write all this test software. And then you would spend hundreds of thousands of dollars of equipment. And not only would you design at the same time, but then you spend all your time writing all this test software, right? Only to throw it over the wall to the next silo to let them do the testing again. It's like, this is a complete waste of time. So and
so much money
and time
and resources
and couple it, like what we said with COVID, you're now home by yourself and you are at wit's end. You have no idea what to do now. I mean, you're not going to bring a whole lab into your house, even if you were skilled enough to write all that software and design everything. So what's the solution? So we're now stuck at home. We're by ourselves, like I said, sitting next to our kid coloring at the dining table. And all we've got is, and I'll trivialize it, all we've got is a Arduino that we want to test against. And we've got our analog discovery. So now what I'm doing is I'm trying to engage in this new type of process where it's like, I don't have time to throw this over the wall. I don't have the resources. I don't have the people to throw this over the wall. I need to test this now. So what we do is we design our boards, right? Or we do our prototyping. We do our prototyping and we put everything together and we start driving all that stimulus either before we actually put the prototype together and watch it fail, or in conjunction, which is cheating. It's not really test-driven development, but you do it at the same time. So I'm driving all those signals. I'm reading back everything while I'm designing my prototype, and then while I'm reworking my board, and then while I'm writing my software drivers to interface with all those chips on the board. And I'm doing that step by step by step. The most important part is once you've reworked the board, right? To make sure that I haven't messed, if I rework something over here, I want to make sure I don't break anything over here. You want to do regression testing, which in hardware is, if a design engineer is sitting there, probing, turning knobs for the 100th time, they're going to get really frustrated and just skip, better is the enemy of good enough. But in this case, it was not good enough. And then you've blown the board. So you run all this hardware automation, all this testing in a regression fashion, go get yourself a cup of coffee, and 3 minutes later, it's done. And you've basically guaranteed that, let's say, hypothetically, 75% of your board is like perfect. And it cost you a couple $100. And you did it from your living room with a bunch of Crayola crayons. Yeah, with a bunch of crayons in the mix.
Which is just awesome. Like, that just makes perfect sense to me. So let's talk more about that solution. So what are you've talked about Arduino, you've talked about the analog discovery, and kind of this process. And then you said you only have to write a little bit of code. Does it matter, like, what software? Is this limited by software code? What kind of software is generally used? Again, coming from a place of non-embedded engineering background.
So, I mean, there isn't really like an industry standard in terms of how you want to do things. Like I said, a lot of people use Python. You could do stuff in C. You could use different test frameworks. I happen to use a test framework called PyTest because I use Python. It's all over my articles. You'll see it. But it's because it's been tailored towards the maker movement and mostly university students. They've tried to dumb it down as much as possible. And so, like in some of my examples, in this particular article, I've designed and cross-compiled this for like pretty much any target. So you can run this on a Linux laptop, a Linux desktop. You can run this on a Raspberry Pi. You can run this on an Orange Pi. You can run this on pretty much any platform with having this same exact test setup, the same exact ecosystem. Because now, we're moving to different platforms. We're cross-compiling. We can build the same base solution and deploy it to many different things, whether it's deploying to a desktop or a web application or a hardware device or a mobile app or whatever it is. That's that's the key these days is build once and deploy many. And you see it all over the software world with the apps and all.
Yeah, it's true. I do. Even here at Altium, you talked about if you fix something over here, something over there. I hear our internal developers talking about that. Like, I'm like, why don't you just fix that one bug? And they like, well, we would, but we have to address this whole quadrant, right? Or we break stuff over there. So it's not a simple problem when you're developing software that way. Okay. You had shared with me kind of a scenario that you've gone through personally at the company you're with now, but you said you've run into this scenario many times across several companies. So can you give us like a real world example, from a position of professional engineering?
Yeah. So right, exactly like you said, I've seen this problem really in almost every company I've been at, or friends who are at other companies, particularly really in embedded systems, but this can pertain to general hardware development or software development. So I walk in day one and we have embedded software engineers working on hardware. Now, of course, the boards just came back from manufacturing and the boards are brought up. The hardware engineers have done their due diligence. They've checked all the interfaces. Seems relatively good. But when you're talking about an embedded system, there are limitations to really flushing out a board until you've written the code to, exercise, the operations of the ICs. I mean, these ICs, think about them as like brains,
Yes, and absolutely.
If you just, tell a brain or a mind to just sit there and do nothing, they're going to do it pretty well. And maybe you tell them to put a smile on their face. But if you tell them to start doing different things and so you have to then assess the capabilities of whether that person can actually do that. And that's kind of the software in the embedded systems. It's assessing and pulling out the full potential out of what's in this brain.
Yes.
And so
it's programming that brain so it does
what it says.
It's not just sitting there flat.
Yeah,
right. Exactly.
So the hardware checkout went okay. And then the software people started writing the drivers. The problem is, and you see this everywhere, is that now bugs start to happen. And of course, the software people are complaining to the hardware people because they say, no, you guys obviously, I mean, I don't know so much about hardware, but obviously you guys designed it incorrectly. And then the hardware guys say, guys, it's the laws of physics. You're software people. Software always has bugs. You guys are wrong. And there's this perpetual ideological, philosophical, whatever you want to call it, argument that always happens in the world of embedded systems, which is hardware guys are wrong and hardware guy says the software guys are wrong. And of course, nobody ends up being right.
Sounds like U.S. politics.
Right? So the way to resolve this is to get it right, obviously, and check it. So the software people finally get it working, right? And then the hardware people realize there are some bugs and, some issues and they have to rework the board. That's fine. So then we have it working and everything's fine. Perfect. Not a problem. The problem is when a new problem arises. So now somebody's introduced a bug in the driver or the software. And of course, first thing that somebody else on the team says is go to the hardware guys because obviously there's more rework. And so what happens is you have these software people manually testing everything, handing it to the hardware people, manually testing everything, but then they only test the stuff that they fixed. They never tested all the other interfaces. So
I see.
For example, they've fixed, let's say, an ADC, right? And they're not testing the communication devices. They're not testing the USB ports. They're not testing the Ethernet drivers. None of that. And so now the hardware guy accidentally, there's a solder bridge on another IC that the software person thinks is a hardware, rightfully so, is rightfully so disabling or messing up, the hardware side of things. So now the hardware person has to figure out what's going on. The software person has to figure out what's going on and why something else now broke, the unintended consequences, like what you're saying.
Yes, unintended consequences.
So what do we do? So what I did was, again, I was at home. There really was no option of hiring a whole test department, and not enough time too. We're
right.
We're,
yeah. And then you've got the managers and breathing down your neck because there's time to market and there's budget and budgets exceeding blah, blah, blah. You know the mess.
Exactly. And so there's so many challenges trying to move at light speed, at warp speed. So,
right.
So what did I do? So I said, let's try something. What we're going to do is we're going to take devices like this, Analog Discovery, other devices too that I found, on Amazon and eBay, so like cheap stuff, easy, quick and easy to get. And I wrote a bunch of automated testing, in addition to, because I got caught in this maelstrom because I'm the FPGA designer and I'm writing some of the software and I'm helping with the hardware design too. And I'm just caught in between everyone and say, all right, try to fix this, try to fix that. So I said, forget it. Let's take a different approach. Let's get some low cost devices. Let's all prototype this at home. And then we'll bring it into the lab and we'll start doing all this automated regression testing, hardware testing. But instead of spending years and hundreds of thousands of dollars in equipment, how about you give me a budget of $500 and I'll put it together? Well, that's not true. 550 because I had to spin a custom board that I had manufactured, for very, very cheap.
Yeah.
And of course, I'm at home. Not much to do, not a lot of places to go out at night. My son's gone to bed. My wife's doing her own thing, so I'm soldering all the boards and putting stuff together, a little adapter boards that'll go on my Raspberry Pis and Arduinos. And I start putting all this automated tests together. And lo and behold, couple weeks in, couple months in, time and time again, people are making commits, people are pushing their code, or people are updating the hardware, and we're running all this regression testing. And lo and behold, they fix one bug, and then another one comes up. It's like whack-a-mole. And me, silly me, thinking that I must have designed something wrong in the test system, it must have been my fault. I tell them, oh, no, your bug, it's probably not a bug on your side, it's probably on mine. Time and time again, all my regression testing kept telling me, hey, wait, stop, something's wrong, but I kept dismissing it. And we found lots and lots and lots of bugs and lots of unintended consequences until finally it became like the gospel. A $500 test setup became basically the gospel. That's like a gate. So whenever...
That's crazy.
Yeah. So
crazy, awesome. I mean, but unbelievable.
Yeah. And it's amazing how much you can do with so little. I mean, like I said, just at home throwing together. And now it's an amazing gate that we have just for like a very, very basic, quick, rapid checkout.
That's amazing. Okay, so this is why we wanted to have you on, Ari. So, okay, people can check out your article, right? Will that article give them more kind of like how to, like, how do you pass on this wisdom and this learning now? Obviously an article, but I guess, as we wrap up here, I'm like, okay, we've convinced everybody who's listening must do this. So how do they onboard this?
So again, a lot of the manual process of this, like university students are even already familiar. They're already familiar with Arduinos. They're already familiar with these devices. It's really kind of taking all of that, pulling all those pieces together and getting the automated flow. In my article, I link to a repository that I have on GitLab. And what that basically does is I've set up all my code. I've set up the whole project. I walk you through it. And then what it does is I've committed my code, and it actually, GitLab.com, goes and turns on my devices at home and starts running all of that automated hardware testing. So you can see all the testing. You can see everything that's going on. And then you can implement that. I mean, it's open source. It's completely out there. You can literally copy and paste that to your environment, whether you're using GitHub and Actions or Jenkins or Bitbucket and Bamboo or whatever system, your favorite system at home. You can integrate that with the software folks and get all your automated hardware testing in the loop. So your software guys stop blaming the hardware guys for messing up
That
the boards.
is the goal of this podcast. We want to get the software guys off our friends, the hardware designers. or at least get them, calling a truce and everybody moving to the center of politics and being reasonable
Exactly.
and working well together.
Exactly.
Well, Ari, this has been so valuable. Thank you so much for sharing
you.
it. And thank you for teaching me. My head is spinning, but I'm sure our listeners are going to love hearing this. So for our listeners, by the way, I'm going to link everything I can in the show notes. I don't think Ari's, by the time this podcast is published, I don't think the article will be out, but I will link to the Altium resource page to Ari's author page there. And so just go there. He has other great articles about GitHub and just different great articles that I know you enjoy. And probably within a week or so, you'll see this article. And then Ari will give us his email. He said, Ari, you're good. You said you're happy if people want to reach out to you through Gmail or
100% through my email
or
LinkedIn. Yeah, absolutely.
And, one of the reasons I'm so fond of Ari is he's so passionate about this. I think he does this stuff in his sleep. It's really not only his profession, but it's his play too. So anyways, don't be shy about reaching out. He's been a wonderful kind of champion in the Altium designer community. And Ari, we really, really, really appreciate you and all the value you bring to our community.
Thank you. Thank you, Judy.
For our listeners, make sure you check out the show notes. We'll put lots of links for you there. Thank you so much for spending a few minutes of your day with us this week and hearing from Ari Mapur. I hope this has been valuable to you. We will see you next time. Until then, remember to stay healthy, stay safe, and always remember to stay on track.